Michał posted, so finally it's here. The VQE explained uh, blog post from Michał Stenquist. So um, the backstory on this is that Michał basically said a while back that he's working on a VQE post, and that kind of basically was at the same time when I was getting started with VQE. So I was kind of waiting for this. Finally, it's out 16 hours ago, and it already has an impressive 237 views. That's because if you compare this to his, like I said, that's like 1,600 views, but that's like 570 views. The making sense of popular QC articles. But I have to say that's pretty impressive. So let's take a look and see what's inside. Bam. Okay, so it's a 12 minutes read, but I'm gonna probably take twice as much. Just going through this not quickly, but like in detail. What am I expecting? I'm expecting, I think, a sort of a general overview. Nothing extremely technical. Maybe with a bit of code. I don't know. We'll see. But based on what I am right now in my learning, I think in my exploration, I expect this to help me crystallize, the concept a bit more. So I've spent quite some time on VQE, QAOA. I'm currently doing a series of videos on a continuous variable version of QAOA. So let's see. Just let's first do a quick scan. What does VQE do? Why do we care? The variational. Okay, the variational principle. So that was something that Jack Cerrone also talked about in his blog. What the hell is an ansatz? Okay. Oh, nice. Some graphs. Okay. Cool. Okay. I'm just quickly scanning. That seems like he's gonna try and explain something like about degrees of freedom or something like that. I don't know. Or explore or exploring different sort of space exploration. I don't know. We'll see. What does the circuit looks like? See, I've seen those somewhere else. This style of block sphere. Curious what tool he's using to create those. Okay. Why my scrolling is not working anymore? Okay, now. A hybrid approach. Why is this appropriate for NISC devices? Okay, interesting. And oh, an example. Okay. I think I've seen that somewhere else as well. Is it in the original VQE paper? Oh, yeah, the following picture from the original VQE paper. It sounded familiar. It looked familiar. Okay, so there's a link to a Jupyter notebook with PyQuil. Okay, so that's the original paper of VQE. No, but I haven't really read that. Okay, I think I might have seen that somewhere else in a blog post or something. Could probably read the original paper. Okay, so there's a notebook which is a supplement to my blog post about VQE. Okay, cool. So what is it about? We'll probably go through this. It's rather short, so we'll probably go through this as well. Let's go back to this and closing notes. Okay, let's see. Let's just go through this. Okay, so dear reader, VQE, variational quantum consolidation, and QAOA, quantum approximation are the two most significant near-term quantum algorithms of this decade. Those are big words, though. If you're interested in this field, you might have come across these terms along with variational algorithms or hybrid quantum classical algorithms. Yes, that kind of pretty much summarizes my encounter with those names. This will be the first blog post from a series. Oh, so that's going to be a series. Okay, interesting. Aimed at helping you understand some of the intricacies of VQE and QAOA and demystifying how variational quantum algorithms work. This is how I imagine the series. The VQE, how it works. This is the one you're reading. QAOA, how it works. VQE, challenges in progress. QAOA, challenges in progress. Okay, so I'm looking forward to the series actually. Uh, I'll, depending on how fast you get those posts out, I'll probably have moved on to something else already, but I'll definitely do one-off videos on those, just to kind of help me refresh and crystallize knowledge. I think that the posts at that kind of level really help with crystallizing. The how it works part will describe some of the fundamental ideas behind the algorithms and challenges, and challenge progress will discuss the progress and improvements in the basic versions of the algorithms, along with challenges still that the researchers still face. We'll see how it all works in practice. For today's article, let's focus on the following topics. What does VQE even do and why do we care? The variational principle, what is an ansatz? What does a circuit look like? What is the hybrid approach? What's this hybrid approach? What is the, why is it appropriate for NISC? Okay. I guess these two questions are rather easy to answer for me by now. So the hybrid approach is the fact that you need some classical post processing and that you don't need a quantum computer for that because they're not the best. Although there are some papers that I read in the past where they explain how to do gradient techniques for optimization directly on the quantum computer. But um, and why is it appropriate for NISC? It's because I think those circuits are not really big, so they are quite resilient to noise, or resistant to noise, or noise friendly. Okay, if you're not familiar with the term NISC, is noisy intermediate scale quantum. So this speaking means near term quantum devices. What does VQE even do and why do we care? Without going too much into detail in the details in the math, I would like to explain that we can use VQE, what we can use VQE for and why it's important. So VQE allows us to find an upper bound of the lowest eigenvalue of a given Hamiltonian. Okay, straight in. Okay, now some definitions. Okay, I see Hamiltonian. That's good. I imagine if I would read that without knowing anything about VQE, uh, that's quite some stuff already. Upper bound, so we have some quantity and we don't know its value. For the sake of the example, let's say it's the level of water in a well. We know that the water surface can be above the edge of the well. If that was the case, the water would spill. So this is our upper bound. We also know that the level cannot fall below the bottom of the well. This is our lower bound. Sometimes when we describe a physical system, it's very hard to find a real value, but knowing the lower or upper bound can help us estimate what the value might be. A Hamiltonian, the Hamiltonian matrix, which describes the possible energies of a physical system. If we know the Hamiltonian, we can calculate the behavior of the system, learn what the physical states of the system are. It's a central piece of quantum mechanics. It's a compact definition, but I think it's. I always, I mean, I see it as the way it describes the way the energy evolves. Oh man, it's early in the morning. So, but good. Eigenvalue. A given physical system can be in various states. Each state has a corresponding energy. These states are described by the eigenvectors, and their energies are equal to the corresponding eigenvalues of what? Can be in various states. Each state has a corresponding energy. These states are described by eigenvectors and their energies and are equal to the corresponding eigenvalues. In particular, the lowest eigenvalue corresponds to the ground state energy. I guess eigenvectors of the Hamiltonian? Is it like this? That all the possible energy, that's a question. Is it that all the possible energy levels are actually mapped to the eigenvectors of the Hamiltonian? So this means those are the states that then for which then the Hamiltonian doesn't actually have an effect. Energy levels equal to eigenvectors. Is this true? Oh, eigenvalues of an operator correspond to energy states in quantum mechanics. Why? When finding the discrete energy states of an operator, I have been taught to use a time-independent Schrödinger equation which restates the definition of eigenvalues and eigenvectors. What I don't understand is why the eigenvalues are the energy states. Is there firstly a mathematical reason and secondly a physical reason? Um, this is right from Hamiltonian or Lagrangian mechanics, which I am not familiar with. Has been remarked by others and explained clearly and mathematically. The eigenvalues are important because A, they allow you to solve the time-dependent equation, solve for the evolution of the system, and B, state which belongs to the eigenvalue E. State which belongs to the eigenvalue E. As we say, a state which is an eigenstate with eigenvalue E has an expectation value of energy operator, which is easy to see, has to be E itself. But those explanations are advanced and real on maths, and they do not explain why E should be considered an energy level. Okay. At some risk, I will try to answer your question more physically. Okay, that's not for now. But roughly speaking, it seems to be the case. That's something new. Didn't know that. I thought all we cared was about the lowest energy level, but it seems. I mean, for VQE that's too true probably, okay. I didn't know the eigenvalues corresponded to the actual energy levels. But it's pretty tied to physical systems so far. Ground state. This is a state of the system with the lowest energy, which means it's the most natural state. A given system always tends to get there. Oh, nice. Yeah, nice way to put it here. And if it is in the ground state and it's left alone, it will stay there forever. Yeah, nice summary. That's nice. Okay, so that's a nice breakdown of those concepts. These physical systems and states may sound abstract, so let's try an example that's a little bit more down to earth. I cannot think of anything simpler than a hydrogen atom. So we have a two-particle system with a proton and the center and one electron. We can describe it with the Hamiltonian. The ground state of the electron is its first orbital, and in this configuration it has some energy which corresponds to the lowest eigenvalue of the Hamiltonian. If we hit it with a photon, then with specific energy, we can get it to an excited state, that state that's not the ground state, described by another eigenvector and eigenvalue. Okay. Yeah. So I was checking the comments in the comments in Twitter, and meow, and I have to say that I think it was Bob Suter actually replied saying, I'm interested in having a non-chemistry example, but I have to say that having gone through different examples and different explanations, even that example is really concise and to the point. So I think that is actually helpful. With all that in mind, we can reformulate our statement about the VQE. VQE helps us to estimate the energy of the ground state of a given quantum mechanical system. Estimate providing as an upper bound if we know the Hamiltonian of this system. Yeah, okay. But sure, you can probably, that's chemistry related, but you can then probably, or really physics. You can think of, because really what the Hamiltonian is at the end of the day is just a model, right? It's a mathematical model, and then so what you're saying is that the eigenvalues and eigenstate and the vectors of that Hamiltonian describe some specific properties of the model, which are those energy levels. To be mathematically exact, upper lower bounds are defined for sets, not single values. So whenever I mention upper bound of a value, I really mean upper bound of a one element set containing a given value. Okay. I mean, I don't care anyhow. Also, I know that stating Hamiltonian is a matrix might be viewed as an oversimplification, but I find it a very helpful oversimplification. Me too. It's time to get to the second, arguably more important part. Why do we care? Um, there are at least two reasons why we care about using quantum computers to get energy of a ground state. Knowing a ground state is useful, and two, it's really difficult to obtain it using a classical computer. Ground state energy is fundamental in quantum chemistry. We use this value to calculate the number of other more interesting properties of molecules, like their reaction rates, binding strengths, or molecular pathways, the different ways in which a chemical reaction can occur. Many of these calculations involve several steps, so an error in the first step will introduce an error in all the subsequent steps. Therefore, if one of the values we use in the first step, the energy of the ground state, is closer to reality, okay. But I mean, again, like to this concept. I mean, to this comment. So the thing here is, I think, given the complexity, given the complexity of the topic, it's important that there is an actual end-to-end example you're using. So I think trying to state at a high level and trying to always kind of explain something from different angles, like what a Hamiltonian is actually complex, and if what you're doing is you're trying to create an article like this, which is rather compact. So um, would be helpful maybe, but I don't know. I'm fine with it because I'm at least curious enough that I know that you can extrapolate. I know that you can abstract, and I know that you can always, like, if it works if the model works for some concrete example, you can for sure find other examples that work for the same model. And so and the concept of a Hamiltonian, yeah, you can abstract it into like geometrical transformation or whatever. Like, it is, it is what it is. It's just an I think this is good. I think this is well explained and actually pretty straight to the point from a definition perspective. So what I've learned so far, new stuff that I've learned so far, is that actually the different eigenvalues and eigenvectors map to actual energy levels. I didn't know that. Maybe it could be that I've read that before, but it just didn't it didn't click. So good. The variational principle. There's a bit of a weird uh, font change in here, but that's fine, I guess. I'm really sorry for using. Okay. Why I didn't even read that? I'm really sorry for using a different. Don't apologize, man. I'm really for using a different font in this section, but I'm not an HTML wizard, and this was the best way I found to incorporate equations with nice formatting in this blog post. The same for the later sections. I used built-in symbols where I could, but in some places I had to switch. All good. Um, In this and in the following section, I will go into more technical details of why and how VQE actually works. The first piece of this variational principle. Let's say I have Hamilton H, which with eigenstates, then the following relation holds, which is basically a characteristic equation, eigenequation for H. The problem is that we usually don't know what the eigenvalues, what the eigenstate is. What am I reading? This is what and what's the value of lambda. So how can we get some estimate for that? Well, to get the energy value for a given state, we can use the following expression. We usually refer to it as a calculating the expectation value of H. If we use an eigenstate for the eigenstate associated with the smallest eigenvalue, we would get E0, the ground state. energy. It's by definition the lowest value we can get. So if we take an arbitrary with an associated energy, we know that this is always true. We get equality if we are lucky enough that our state is equal to the ground state. The method described here is known as a variational method, and the following relation is known as the variational principle. I struggle with why is this, because I mean, but Jack was going through the same thing, but I struggle with why is it so important to formulate it this way? I mean, it just seems common sense. I mean, it's just telling you there's nothing, like the lowest energy is the lowest energy. There's nothing lower than the lowest energy. Fine. And if you're doing, okay, so basically if you're doing expectation, calculating the expectation, you're never gonna get below that, because all what you're doing is averaging, so to say. Um, so this is an upper bound for the ground state energy. It's exactly what we wanted. The problem is that just knowing an upper bound doesn't yield much benefit. The closer the upper bound is to the real value, the better. In principle, we could simply try all the possible states and pick the one with the lowest energy. However, this approach isn't very practical. Um, there are way too many states to accomplish that in a reasonable amount of time. Also, most of the values will give you really bad answers. Most of the states will give you really bad answers, so there is no point in trying them out. This is where the ansatz takes the stage. I know I've done a couple of shortcuts here to keep it short and easy to digest. If you want to get a formal proof, okay. Um, what the hell is an ansatz? So, that's Wikipedia. Okay. Where am I now? Here, the ansatz. Okay, cool. Once you start reading papers about VQE and QIA, you will start noticing people care a lot about ansatzes. I have missed the definition of ansatz when I started learning, which meant that for a long time it was something rather abstract to me. So here I will try to give you the intuition regarding this topic. Ansatz means approach in German, by the way. The problem, as mentioned in the as mentioned in the previous section, is that we could like to explore space of all possible states in a reasonable manner. So we do that using parametrizable circuits. I don't know if it's written correctly. I might just too sleepy to pronounce this correctly. Circuits which have gates with some parameters. Okay, so but it's about space exploration. That's what I sense. So let's take a simple circuit consisting of a single RY gate as an example. It has a single parameter rotation angle. Okay, so basically, but it represents a whole spectrum of quantum states, namely these ones. Okay, so that's what you see in the picture, the visualization. Really nice. If you're not familiar with it, you can read about it here, the blocks here. Okay, cool. Yeah, but it's actually, I didn't expect that you would spend some time explaining what it really means to explore the space of solutions, but it's actually neat for um, if you're not familiar with this. However, there are many states that we can represent. In order to do this, we need to introduce another gate, the Rx gate, and of course to find the corresponding angles. So Rx and Ri are examples of simple ansatzes. The situation gets more complicated when we have to deal with multiple qubits or entanglement. I don't want to get into details here. I plan to cover that in the second part of this blog post. There's a great paper that covers this topic in depth, but in general we want to have an ansatz which I didn't. Okay. Expressibility and entangling capability of parameterized quantum circuits for hybrid quasi. Interesting. I might add that to the list of my to-dos. Cool. Covers many states. Ideally, we want it to cover the whole space of possible states. Is shallow. The more states you use, the higher the chance of something going wrong. So we're talking about NISC after all. Yeah, so you have to have less gates. Yeah, doesn't have too many parameters. The more parameters, the harder it is to optimize. Correct. If the description above doesn't give you enough intuition of what it's about, let's try with the following metaphor. Imagine you have a robot. Yeah, I guessed it. So that this is about space exploration. Simple robot with the right arm can rotate around the central point. Let's say the robot has a pen it can draw no matter how hard you try. The most you can get out of it is a circle. So how to improve it? Well, you can add another rotating arm at the end of the first one. Now you can cover much more. A big circle empty in the middle. Okay, and if we have thought that actually the arms can only move in a discrete way, they always rotate by a fixed angle. If it's small, then you can still cover most of the space. If not, well, you will get a nice pattern. Anyway, it might be beneficial to add additional arms in this imperfect scenario to cover the space better. Why don't you add 20 arms? It sounds impractical for several reasons. The more arms you add, the harder it is to construct and control them, and it's more error prone. By the way, you can check this video to see how crazy you could get with a similar setup in theory. That's nice. That's a nice video. Yeah, that's nuts. That's nuts, man. Boo. Are you crazy? Wow. That's a nice thing, by the way. That's a nice video. That's nice. That's nice. Okay. Um, so what does it have to do with our ansatz? Is having a good robot setup will allow you to cover a lot of space, and at the same time it would be relatively simple. Having the same is true for ansatz. A good ansatz is one allows to cover many states, and which there is a lot of parameters. It's easy to, yeah. No, nice. That's a nice explanation. A nice way to explain that. What does the circuit look like? Um, while writing this section, I realized it requires explaining some additional concepts. Uh, if it seems difficult, don't worry. You don't need to understand it fully to get the big picture. If this is too much at once, you can always come back later. Um, as we all know, to do quantum computing, we use circuits. So what does one for VQE looks like? It consists of three parts: an ansatz, a Hamiltonian, and a measurement. We know that the ansatz part is about. It prepares the state we need in order to apply a variational principle. Hamiltonian. There's a limitation on what Hamiltonians we can use with VQE. We need Hamiltonians constructed as a sum of Pauli operators x, y, z, and they're tensor products. So, for example, we can have the following Hamiltonian, or for the multi-qubit cases. Is it that you're talking about the mixer in this case? I don't know, because I thought your ansatz was basically something that approximates your Hamiltonian. What might be surprising is the fact that we don't actually put any of the corresponding x, y, and z gates into the circuit. We use them to choose in which basis we want to do a measurement. Okay. Most, if not all, contemporary quantum computers perform measurements in the so-called computational basis, which what it means is that they tell you whether your state turns out to be 0 or 1. However, that's not the only way to go. What if we want to distinguish between the states plus and minus? Measuring the computational basis, you'll get 0 and 1 with the same probabilities for both of them, so they are indistinguishable. So to see what might help, we can use the block sphere again to visualize both pairs of states. Yeah. So as you can see, both cases they are the opposite ends of the sphere. It means that we can switch between them by performing a rotation around the y-axis. It gives us a tool to distinguish between plus and minus states, and if we can measure only whether the state is 0 or 1. If we start from plus and perform a rotation on y, the rotation, then we'll end up in the 1 state. If we now measure it, we'll always get 1, similar to for the other state. After rotating, applying to all the states, we'll get the following block sphere. Notice the color switch. Thanks. I was like trying to do it. It's like, what's the difference? The color switch. So coming back to our Hamiltonians, the first thing we need to do is divide the sum into its elements, so-called terms. Now for each term, we look at every Pauli operator and append appropriate rotations to the circuit. And rotation if it's x, a rotation y if it's x, rotation x if it's y. We do nothing if it's z. There's some caveat here. We actually don't do it all at once. We create a separate circuit for each term. What? So I think that's something that I was. Okay, so I was missing that. I remember. I vaguely remember something about it. Was like, yeah, you measure that from you measure the ansatz from different perspectives. Okay. In order to calculate the expectation value, that is, right? There is one more caveat here. So, and once we've done this, so I'll get a deal here. Hybrid approach. These devices example. I'll do the example in another video. Uh, so just to keep it, just to make sure the video doesn't get too long. Um, um, Once we've done this, we're ready to perform the measurements. But how exactly do the measurements relate to the variational principle? Remember this, it's created by ansatz Hamiltonian is composed of the sums of Pauli terms. So we can separate it in individual terms and deal with them one at a time. The question at hand is how to get from here to here. Why is it that whatever here and here we can utilize the fact that this represents the expected value of hi, which can be approximated by observing measuring the state many times, like using the right basis, the one corresponding to the eigenvalues of hi, and averaging the result. The more times we do it, the better. Yeah. Okay, but I didn't quite get that that's what you're doing. That you actually need to decompose that. But that then really is your mixing, right? The mixer part. That's where I remember vaguely that I mentioned that in one of the VQ videos where I was like, yeah, at the end you do the answers, but then you gotta measure this on the computational basis of the Hamiltonian somehow. So so what this is saying is you decompose it in terms of the Pauli of Pauli operators, and then you basically um, use that to say now I'm gonna make a measurement on the x basis or the y basis or the z basis. Aha. That's how you do it. Okay. Okay, well that's why in the CB quantum computing version of QAOA or VQE or whatever, you're saying you're basically if you choose position, then you're gonna do whatever position measurement. If you use momentum, you're gonna do a momentum measurement. That's the same concept. So here, if you're interesting. First, okay, but that's definitely helpful. For some details on some helpful derivations, I recommend reading Chapter 4 of Quantum Computing for Computer Scientists. Um, okay. Let's take a look at the following example. Let's say the Hamiltonian is this. There's only one qubit, some omitting indices. It is represented by the following matrix. We would like to learn its ground state using VQE. So to begin with, we need to choose our ansatz. We don't want to overcomplicate it. Let's say our ansatz will be simply Ri. This will allow us to explore the states, cosinus, whatever. Our Hamiltonian has three parts. Bum, bum, bum. The first part is fairly simple. As you recall, if we have a zk, we don't do any rotation. So our circuit for the first part of the Hamiltonian will consist just of the ansatz. Will you account for that too later on? I guess so. You might wonder what should we do with it too. It's just the second time it happens where I ask something and the next paragraph starts with that. You might wonder what should we do with the 2 in front of the z. Um, well, we treat it just as a weight, exactly. Okay, so after we do measurements and we will be calculating the energy, the results coming from H1 will count twice as much as the results coming from H2 and H3. So basically, yeah, so H here is the cost. So that will be kind of your cost function is the Hamiltonian. That's what you're trying to do. You're calculating the energy. Um, okay. But in the cert, read the notes. No, read the docs. There is a bit of a different function here. Because there's also here a tutorial about VQE, but then what's your cost function? Because here I don't. Here you've got a Hamiltonian. Could be interesting to sort out because here you've got a Hamiltonian. The ansatz. Come on. But basically you've got a Hamiltonian here. Where was that? Where is this? Here. That's your Hamiltonian, right? So I don't know how does this map to that, because make a measurement which samples from some terms in H, right? So this is the way, prepare the answer to make a measurement which samples from some terms in H. I mean, first of all, there's still the open ticket here that I don't know why the so-called mixer is applied at the beginning, which shouldn't be the case. But then I don't see here so there's like the first layer of rotations, but I don't see here that. So this is something that I gotta clarify because it's confusing me. I don't see here where that decomposition is taking place, but maybe that's what's missing, or I don't know. Because the energy function, right? The energy function is just calculates the. It just goes through. It basically goes through the Hamiltonian function. It just that's what it does, right? It's adding basically the these, right, and these times H, which is the influence, if I remember well, energy function, total energy. Yeah, something like that. Measurement results. Anyway, the first part is fairly simple, as you recall it from. We have a Z gate. We don't need to add any rotation, so our circuit it just consists of the ansatz. You might wonder what should we do with the two. Okay, so I read that. In case of H2, we have one gate X, so we simply need to add an RY rotation. Why not a Hadamard? I don't know. To our circuit. H3 is the easiest one of them. It's just a constant factor we need to add to our calculations, and we don't need to do any measurements. So in this example, we need two circuits to use our VQE. We can use the following. You can see them below. What about the first one? No, two rotations? Why two rotations? So the one there's no rotation, just a measurement, right? That's H1, and H2 it's one rotation. First RY are. Oh yeah, sorry, that's the ansatz, of course. The ansatz itself it's an RY. Okay, they are parameterized by theta. Second RY in the right picture is actually an RY. But if you use quirk, you can see that in an easier way. Um, the last symbol is how we depict measurement in quantum circuits. Our Hamiltonian was this. So if theta is 0, then we will get 0 for H1, 0.5 for H2, and 1 for H3. So our expectation value will be 1.5. If theta is pi, we get going through all the possible values of theta would be cumbersome. So I will tell you how to approach the problem of finding a good value of theta in the next section. Okay, that's a nice smooth introduction to the next section, but I'll leave it here. So this example was pretty simple, and you might wonder, okay, but how to deal with this case with the case when there are more than one polymatrices with one term? It turns out that whenever you start multiplying polymatrices, in the end you always get another polymatrix multiplied by some constant, so you can always simplify your term in such a way that you will end up with a single polymatrix. And what if I have more qubits? Again, we treat each term separately, perform all the rotations that we need at the end, and measure all the qubits. Perform all the rotations that we need at the end and measure all the qubits that we need. So basically that's the mixer, but it's still, so that's what they call the mixer, but it's still but it's still not clear to me where this is, for example, here in the tutorial. So that's, yeah, I mean that's the mixer, that's what's missing, but it's still not clear that this is used like that. And it seems like there's no mention about these at all here. So I don't know how much strict it is that you gotta stick to those to that type of mixing. Is this the only approach, or can you choose other mixers for that? If that's the right term, I might be getting wrong. That might not be the mixer, but because the cost, you have your cost function, which is I would assume that the ansatz based on the way Jack Sorney explains it and others. So the cost Hamiltonian, that would be your ansatz, and the mixer Hamiltonian is basically the one that allows you to make the measurements, the right measurements. But I don't see this explained here. So I'll have to think through that a little bit more. That deserves another take. But yeah, then the hybrid approach is okay. Probably this is going to be uh, about optimization, and then this is probably going to be about like a bit of the NISQ stuff, so the errors and things, and then we'll go through the example and in the next video. I keep jumping from video to video. I'm sorry, I can't seem to get things done, but I'll get things done eventually with VQE and QAOA. I'm spending quite some time on those, but it's definitely it definitely takes time to help those little things crystallize, you know, because sometimes after those videos I think I know it, but then I do something else and it's like I don't really know it yet, and so um, that's why those things, reading those kind of papers of posts is really helpful. Perfect.